Hello guys, good evening. Let me take a picture of the attendance. And Tuesday, we have learned the basics of probabilities. Hello everyone. Yeah, Tuesday we have learned the basics of probabilities. I hope you still remember what is classical probability and what is empirical probability, and we know how to compute the values for each definition of probability. Okay, so today we are going to cover section 4.2. Today we are going to cover section 4.2, addition rule and multiplication rule. So first concept, compound events. What is a compound event? A compound event combines more than one event. We only more than one events. Yeah, we are going to talk about two types of compound events only. The first one is A or B. A or B. The second one is A and B. A is an event, B is an event. But A or B also represent an event or result of the procedure. So A or B is also an event. It refers to the result of a procedure that A occur or B occur or A, B both occur or both occur. Or both occur. So that's today's focus. We are going to talk about how to find the probability for compound events. How do we find the probability of A or B? How do we find the probability for A and B? A and B refers to the result of a procedure that A, B both occur. A, B both occur. So today's focus is to find the probability of A or B, also find the probability of A and B. And let's look at A or B, the or here, the logic connective OR. OR here is inclusive or, not exclusive or. So I can give you an example about exclusive or. Let's say you go to a restaurant. You go to a restaurant and the waiter tells you that if you order this special meal today, then you will get a free salad or get a cup of soup for free. So salad or soup. So the or she mentions, the waiter mentions, he mentions is exclusive or. Okay, exclusive or means they cannot both happen. You either get a salad or you only get a soup. You are not getting both. Does that make sense? So or has two types. Yeah, or has two types. Exclusive or means only one can happen. Yeah, they cannot happen both. Yeah, like you get a free salad or get a free soup. Yeah, what he really means is one or the other, not both. That's exclusive or. But in probability, in statistics, here or is inclusive or. Inclusive or means A or B means A occur, only A occur, or only B occur, or both occur. It's possible for them to happen at the same time. both happen. So that's how do we understand the logic connective OR connected to events A or B. So earlier I mentioned the focus of today is to find the probability of A or B. Also find the probability for A and B, right? Yeah. To find the probability of A or B, we need to use the addition rule. So addition rule is to find the probability of A or B. And multiplication rule, the title of this section is addition rule and multiplication rule. Yeah, addition rule is for find the P of A or B. Multiplication rule is to find probability of A and B. So let me give you the two rules. Addition rule has two formulas. The first formula, P of A or B equals P of A plus P of B minus P of A and B. A and B is the result of the procedure in which both A and B occur. Yeah. So that's the first formula of addition rule. Addition rule has another formula. Another formula, in fact, is a special case. A probability of A or B when A and B are disjoint. Yeah, in a special case that A and B are disjoint, probability of A or B equals P of A plus P of B. So those two formulas are addition rule. Okay, very, very important. The second formula is simpler, but we could only use the second formula when the two events are disjoint. Let me explain what is two events are disjoint. The first case, if I use a Venn diagram to describe, if we let A, the set of A, represent event A occur, set of B to represent event B occur, they could overlapping, right? They could overlap. So that's the first case. And second case, the special case, A and B disjoint means the two events not possible to happen at the same time. They do not have any outcomes in common. Okay? Remember events. Remember, a sample space is a set of all the outcomes. And events actually are subsets of the sample space. So we could totally use the set theory to study probability. Yeah, you can, I definitely think you see the difference here. Yeah, let me write down the formal definition for disjoint here. Formal definition for disjoint. A and B are disjoint if it is not possible for them to occur. It's not possible for both of them to occur or at the same time. Example, let's think about rolling a die. If I let A get a number bigger than 3, and let B be the event that we get an even number, and you help me to determine are A and B disjoint or not. And I'm going to give you C and D as well. If I let C be get a number odd, and D, I'm going to use B again because I have B already, is the event that will get an even number. Okay, so A and B are disjoint means the two events not possible to happen at the same time. It's not possible for them to occur both. Yeah, it's like they are enemy. If A happen, then B cannot happen. If B happen, A cannot happen, right? Something like that. Yeah, the two things are like enemy, never be together, never have any in common, never have any outcomes in common. So in the procedure rolling a die, if we let A be the result that getting a number bigger than 3, and let B be the result getting an even number, do you think A and B are disjoint or not? No, you are right. They are not disjoint, all right? They are not disjoint. Because it is possible for them to happen at the same time, right? Yeah, bigger than 3, start from 4. 4 is fine, 5 is fine, 6 is fine. And even numbers, 2, 4, 6, they do have a common outcome, which is 4 and 6. Yeah, very good. What about C and B? If we let C be the event that getting an odd number, if you roll a die, and B is the result that you get an even number, are B and C disjoint? Yes, they are disjoint. Very good. You guys great. Perfect. Well, then let's see, how do we find, let me erase this. I'm gonna read them again later. Yeah. Now let's use this procedure to find probability of A or B and the probability of B or C, okay? Probability of A or B. Whenever we need to find the probability of A or B, like the or of is called disjunction of two events. We need to firstly ask a question: are those events disjoint or not disjoint? Yeah, since you are answering me, yeah, A and B are not disjoint, and you know what? We use the first formula. Okay, we're gonna use the first formula. So we have P of B or B, P of A or B equals P of A plus P of B minus P of A and B. All right, yeah. So let's see. Rolling a die. We remember sample space, right? The sample space contains 6 outcomes. 1, 2, 3, 4, 5, 6. And this is classical. Yeah, it's a classical. Then anyone can tell me what's the probability of A? What is the probability of A? Getting a number bigger than 3. Classical model, half. Awesome. Yeah, the probability is not 3. Remember, probability is a value between 0 and 1. Probability is a value between 0 and 1, bigger than or equal to 0 and less than or equal to 1, right? Yeah, but I know what you mean. You mean even A contains 3 outcomes, 4, 5, 6. But we also have the denominator. We have to divide 3 by 6. Yeah, right, you got it right. 1/2 is 3/6. And you know what? I would like you to keep 3/6 because you will see why in a moment. All right? Yeah. The denominator is the total number of outcomes in the sample space, so 6. And the numerator is how many outcomes favor A occurring, so 3/6. And what's the probability of B? Rolling a die and get an even number. Yeah. 2, 4, 6. So 3 of the outcomes favor the event B occurring. Denominator is also 6, right? Yeah. It's also 3/6. Very good. Half. Perfect. What about the probability of A and B? Yeah. Let's think about how do we describe the result A and B. We roll a die, and the result is we got an even number and bigger than 3. So the denominator, since it's still the same model, same classical model, the denominator is still 6, right? Yeah, what matters is the numerator. Yeah, we roll a die and we got a number. The number is even and bigger than 3. What do you think? Is even and bigger than 3. So do we have 2 outcomes favor that result? Yeah, awesome. 2/6, perfect. Okay. Yeah, now you see the reason I want you to keep the denominator at 6 the whole time, right? Because when we add or subtract the fractions, we want them to have the same denominators. Yeah, which they do because they are at the same model. They are in the same classical model. So I would not simplify until the last step. In fact, I ask my students to do this. We are looking for P of A or B, right? Draw a longer bar, and the total number of the sample space, total number of the outcomes in the sample space is 6. So just put a 6 under. And in numerator, we're gonna have 3 things. The first thing is how many outcomes favor A. 3 outcomes favor A. How many outcomes favor B? 3 outcomes favor B. Minus the number of outcomes favor A and B. How many? 2 of them. Right? Yeah. My student, my previous class student, they like this. They don't even have to operate the fraction anymore. Okay, then let's simplify. Numerator, 3 plus 3 is 6, 6 minus 2 is 4. And then we reduce 2/3. Yeah, reduce the last step. 2/3 is the fraction, is the probability of A or B. And we found the probability of A or B. And we use the first formula of the addition rule. We use the first formula when the 2 events are not disjoint. When they are not disjoint. When it's possible for them to occur at the same time. All right, so that's the first formula. Let's see any questions here. The odd, would it be 4 or 6 since events are, and what is that? What is 4 or 6? Yeah, the answer is 4/6. Reduce it to 2/3.
Can you put it back on that screen, the other screen? No, because it's doing the P, the probability A and B. Well, A is everything that's greater than 3, so that would be 4, 5, 6, and then evens. So wouldn't that include the number 2 die as well as part of the even group?
Mm-hmm.
So wouldn't that be 4/6?
Oh, I know what you're talking about. Yeah. Yeah. You can do that for sure. So you're thinking about the result A or B. So bigger than 3 or even. So you have the 2, 4, 6, and then bigger than 3, you have a 5. So it's a 4/6, and 2/3. Correct. You can do that for sure. Yeah, that's very good. That's very good. Yeah. What's your name? It's Dustin. Perfect. That works. But if the problem is more complicated, you would have to use the formula. And the reason I use this formula to find the result, because the purpose here is to use the formula. The purpose here is to use the addition rule. Do you understand my point here?
Yes, ma'am.
Yeah, okay. But your method is perfect. Yeah, your method is perfect. You see A or B as the result of the procedure, and then you figure out among the 6 outcomes, how many of them favor A or B, right? And then just use the classical model to get a problem done. Perfect, very, very good. But our purpose here is to use the formula, because when the problem is more complicated, it's really hard directly to do that. Also, yeah, it's very hard to just directly to find a numerator. Very good. And now let's see how do we find the probability of B or C, okay? P of B or C. As I said earlier, whenever we need to find the probability of B or probability of the or, you know, A or B, one event or the other event, we need to ask the question, are the two events disjoint? We already agree they are disjoint, right? Okay. Then if they are disjoint, to find the P of A or B, we use the second formula. Yeah, the second formula simply, yeah, what's the difference? Look at the two formulas. What's the difference between the two formulas? On the right side, the only difference is the second formula do not have this term, right? Why? Because when A and B are disjoint, A and B cannot occur at the same time. A and B is impossible to occur. So probability of A and B is 0. That's why we don't have that term anymore. All right, so that's the reason. Okay, so use addition rule for probability of B or C. Since B and C are disjoint, and we use this second formula, P of A plus P of C. Very symmetrical formula, right? Okay. And we can do the same thing, use the same denominator because they belong to the same model. Numerator, we got numerator. How many outcomes among the 6 favor get even? Right? Yes, 3 of them, 2, 4, 6. And C, how many outcomes among the 6 outcomes in the sample space favor getting odd number? Also 3, right? Yeah. So we got a 6 over 6, we have a 1. And you know what? Dustin might say, I know 1, the very beginning, I don't have to use formula. Yes, I agree. Because B or C simply means you roll a die and you get even or odd. It's certain to occur, right? It's certain to occur. Yeah. Again, we are just using the formula. Yeah. When the problem is more complicated, we would have to use the formula. So that is addition rule, guys. All right. Let me summarize just quickly. Addition rule is to use, we use addition rule to find the probability of A or B. A and B are two events. Yeah, OR. Be very careful when we say or. Yeah, when we say OR or when we say AND, because they are so different. There are two different logic connectives. Yeah, we use addition rule to find the A or B. Yeah, every time we are asked to find the probability of A or B, we need to first determine, are those two events disjoint or not? If they are not disjoint, use the first formula. If they are disjoint, use the second formula. Okay, we are not going to prove them. If you are interested, you can email me, I can explain. Yeah, the reason is because we since they occur at the same time, they have common outcomes. So if we add a P of A and a P of B, the middle part, the overlapping part, would be double counted. Yeah, we don't want to double count it. We only want to count the outcomes in that area one time. So that's why we have a minus probability of A and B. That's the reason. And if the two events are disjoint, then we use the second formula. That is addition rule. Yeah. Today the title of the section is addition rule and multiplication rule, and that is addition rule. Addition rule is used to find the probability of A or B. Okay. Next, we're going to look at multiplication rule. Okay. Multiplication rule. We also have two formulas. Yeah. What do we use for multiplication rule for? We use the multiplication rule to find the probability of A and B. Sometimes, yeah, is possible, is easy to just find the probability, right? Yeah. For example, earlier, B and C. What's the probability of B and C? Can anyone answer me that question? Rolling a die, B is getting even number, C is getting odd number. What's the probability of B and C? Yeah, what's the chance that getting a number and that is even and odd at the same time? 0. Isn't that supposed to be 0? Am I clear about my question? B is getting even number, C is getting odd number. So what's the probability getting B and C, getting both at the same time? Not possible. Yeah, you are right. Not possible, right? Yeah, it's 0. Yeah. So I mean, sometimes you can directly find a value. Yeah, but more cases we have to use the formulas. So multiplication rule is to find the probability for A and B. Yeah, and we have 2 formulas for that. Let me write a formula, okay? Yeah, let's write a simpler version formula first. Independent. Multiplication rule you can see is multiply, right? Yeah, that's the first formula. And second formula, when the 2 events are dependent. And that formula doesn't work anymore, we have to figure out the other formula. It could be this, but we mainly just do one. I'll explain. Depends on which event occur first, which event occur after. Yeah. So we used to do mainly do the black one. All right. So you see 2 concepts, dependent and independent, right? Okay. Let me explain. What is dependent? What is independent? A and B are independent if the occurrence of one event does not affect the occurrence or the chance of the occurrence of the other. Then we say A and B are independent. We can find some similar idea or concept in real life. For example, if you are independent financially, okay, how about you and your spouse are independent financially? That means you can buy whatever you want. You don't have to worry about your spouse's opinion, right? Yeah. So one event occur does not affect the chance of occurrence of the other. Yeah, they do not affect each other when it comes to chance of occurring. All right. Yeah. Let me put it this way: A and B are independent if they do not affect each other when it comes to the chance of occurring. Yeah. Example. Let's see, how do we understand? Okay. Otherwise, they are dependent. Okay. Otherwise, they're dependent. Okay. Let me give you an example. I know everybody here, they like donuts, right? Let's say you only have 4 donuts, and let's say you love chocolate, and this one is chocolate. How about 2 chocolate donuts? Okay, the other 2 is the other flavors. Okay, yeah. So our procedure here is randomly pick a donut. Yeah, let's say the 4 donuts are in a box. You close your eyes when you grab one, and you don't know which one is which one. You just they have the same size, right? So you just pick one from the 4. You don't know which one. You could have picked I need to figure out the name of that. Let's say vanilla, white chocolate. No, hold on. Lemon. Okay, let's say that's lemon. Okay, as lemon flavor and chocolate flavor. Glazed. Okay, awesome. Yeah, glazed is also good. Yeah. Let me use the lemon though. Yeah. So 2 lemon flavor, 2 chocolate flavor. So you close your eyes, you just grab one. You don't know which one. So that's the procedure. Randomly pick a donut, okay, from the box. We're gonna consider. So that's the background. That's not actually procedure. We're gonna consider 2 procedures. The first one, or 2 cases, okay? The 2 cases. The first one is no, my bad. We are going to randomly pick 2 donuts from the box, okay? Yeah, the first one is the with replacement. The second one is without replacement. All right, yeah. So we let A, B, the first time get a chocolate. We let B be the second time get a chocolate. I might misspell the chocolate. Yeah, just bear with me. Yeah, you mean chocolate. So let's see. Are A and B independent in the first case or dependent in the first case? And also determine, are A and B independent in the second case or dependent in the second case? Okay, let me explain what's going on here. So we have a box. The box has 4 donuts, 2 lemon flavors, the other 2 chocolate flavors. So we are going to do this kind of experiment. We consecutively pick 2 donuts, not together, okay? Yeah. Pick 2 donuts in a row. How about that? In a row. You pick 1 donut and then you pick another. All right. So that's how do we pick the 2 donuts? Yeah. But the first case is we do replacement. Means the first time we get a donut and we look at what kind of donut and we put it back, and then we pick the second donut. Okay, with the replacement. Or you can understand that as the first time you pick a donut, whatever the flavor, you eat it and then you refill with the same flavor donut, you put it back. Yeah. And the second case is you pick a donut first and then you ate it, and then you put it you cannot put it back because you ate it. So and then you pick the second donut. Do you guys, am I clear about this? What's going on? So basically we have 2 procedures. We want to determine if A and B are independent in each case. All right, thank you. So let's see, are A and B dependent or independent in case 1? What do you think? Do you think A and B are independent in case 1? Because the first time you got a chocolate flavors, chance is half, right? Yeah. And then you put it back. When you pick the second donut, you still have 2 lemon flavor, 2 chocolate flavor. So the chance of getting the second chocolate, yeah, the second time get the chocolate, it doesn't get affected by if this occur or not occur, right? Do you see that? A and B are independent. Yeah, okay, with replacement. Thank you, Kelly. Exactly. Yeah, Miranda also answered independent. Very good. They are independent. You know why? Because you put it back. So when you take the second chocolate, when you take the second donut, everything recovered to the original condition, right? So B will not be, the chance of B occurring will not be affected by A. Yeah, A occur or not occur in this first time, doesn't matter, does not affect the chance of B occurring. All right, and what about the second case? Without replacement, you pick a donut and you eat it, doesn't matter what flavor. And then you pick another donut. So that's what you do in the second procedure. And in that case, are A and B dependent and independent? And why? Without replacement, they are dependent. Awesome. Yes, exactly. Why? Because if the first time you ate a chocolate, yeah, so let me show you this. In case 2, okay, I'm gonna do this without replacement. If the first time you got a chocolate, then the chance of get a second chocolate, yeah, let's see what is that. This notation is a conditional probability. Is a concept we need to learn today. You see that? This is, you see this probability P of B given A. Yeah, that bar, the vertical bar is called a given, is described as given. So this is P of B given A. After given is the condition. So A is the condition. So we're considering if the first time A occur, what's the probability of B, right? Yeah. Suppose the first time you ate a chocolate flavor, then what's the probability of the second time you also get a chocolate donut? So we had 4 donuts, right? So suppose the first time you got a chocolate donut and you ate it. So now in the box, how many donuts left? 3. Awesome. So the denominator gonna be 3. Your sample space shrunk. Your sample space shrunk. Your sample space was 4 donuts, but now it becomes 3 donuts. Very good. Among the 3 donuts, how many of them favor chocolate? Again, you are the 8 chocolate. 1. Awesome. You guys are great. So the probability is classical, right? Probability is 1/3. And now let's consider, what if the first time you did not eat a chocolate donut, you ate a lemon flavor? You ate a lemon flavor. It's possible, right? Because you're closing your eyes. You may pick a chocolate, or you may pick a lemon. You don't know. Yeah. So what if the first time you did not get a chocolate, you got a lemon? So A bar occurred already, right? Given the condition that A bar already occurred, let's see what's the probability that second time you get a lemon. Second time you get a chocolate. So since the first time you ate a chocolate, oh my gosh, I'm sorry. Since the first time you ate a lemon, you also have 3 donuts left in the box. Among the 3 donuts, how many of them are chocolate? This time you ate a lemon. Awesome, you guys great, 2. You see the 2 probabilities different, right? Yeah, the 2 probabilities are different condition. That means what? That means A occur or not occur does affect the chance of B occurring. Does that make sense? Make perfect sense, right? So that's the reason without the replacement, dependent, but with the replacement, independent. You probably want to remember that because always like this, okay? Maybe it's not donut, maybe marbles, maybe cars. Yeah, if If it's without the replacement, is dependent. If it's with the replacement, they are independent. Okay, let me give you one more example about independent. Let's say you have a coin. You are going to flip the coin for 10 times. And we normally call those 10 tosses as 10 trials. Okay? And we assume is a robot toss the coin. So we do not consider psychological, emotional factors. Okay? Yeah. Then the 10 trials are independent. Since the 10 trials are independent, the result of each trial are also independent. Yeah, we will see something like that as well. Okay, so when it comes to independent. All right, so I think we understanding what is dependent and independent now, right? Yeah, and let's go back multiplication rule. Multiplication rule. We use the multiplication rule to compute the probability of A and B in the complicated cases. Yeah, and we have two formulas. So before we go ahead to compute the value of P of A and B, we need to ask a question. Are the two events dependent or independent, right? Yeah. If the two events are independent, use the first formula. If the two events are dependent, use the second formula. Okay, yeah, the second formula involves a conditional probability. Yeah, now let me spend just a little bit of time to cover what is conditional probability. All right, yeah, let me give you another example. Let me explain what is a conditional probability. Firstly, let's see the notation of a conditional probability. P of A given B. This is called the probability. This notation represents the probability of A occurring given. Yeah, remember the bar, the small vertical bar is called given. Given even B already occurred. Okay, yeah, we can understand conditional probability as a probability with a condition. With condition. What's the condition? Condition is behind a bar. Yeah, you put a condition behind a bar. Yeah, given B already occurred. Yeah, based on that condition, what's the probability of A occurring? All right. So let me give you an example. Yeah, I like to use the rolling a die to explain the concept because it's so simple, right? Rolling a die. Sample space is a set containing 6 outcomes. And we are going to consider these two events. And we are going to compare and contrast those two probabilities. Okay, this one is the simple, just a normal probability. And this one is a conditional probability. Let's see what's the difference between them, okay? Rolling a die. A represents the event getting number 6. B represents the event that getting an even number. Well, anyone can help me to find the probability of A. Roll a die and get a number 6. We should know that, very straightforward. What's the probability of getting a number 6? Perfect, perfect, awesome, 1/6, yeah. Awesome. And now let's consider this conditional probability. Conditional probability, yeah. The probability of getting number 6 given, we already know the number is even. Yeah, we already know the number is even. Now, of course, we would not consider 1, we will not consider 3, we will not consider 5, right? So when we attach a condition to the probability, we actually shrunk the sample space with the condition. Let me write it down. With the condition, the sample space shrunk to a different sample space now. 2, 4, 6. Do you agree? Yeah, because we already know the even, it's not odd. So of course we will not consider 1, 3, 5. So we only would consider 2, 4, 6, right? Yeah. So kind of, we understand that as when we have a condition attached to the probability that we consider, the sample space shrunk to a smaller size sample space. So the denominator not 6 anymore, denominator is 3. And among the 3 outcomes, how many of them favor number 6? So the probability of A given B, the probability of A given B, the probability of getting number 6 given the number is an even number, is 1 over 3, is bigger than 1 over 6. Do you see the difference? This and this, they are different, right? Yeah. This is a normal probability without a condition, and this is a probability with condition. Yeah, they are different. Yeah, I want to use this example to explain the definition of a conditional probability. We got an idea earlier when we pick up the donuts, right? Yeah, here is also to explain the concept of conditional probability. Am I clear, guys? Yeah, let me know. Are we good with the 2 formulas with of the multiplication rule? Thank you, guys. Yeah. So let me summarize a little bit. Yeah, summarize a little bit about multiplication rule. Multiplication rule is to find the probability of A and B. Whenever we need to find the probability of A and B, we need to consider, are those 2 events dependent or independent? Yeah, we already understand the difference between independent and dependent. If it's independent, the formula is so simple, right? Yeah, if it's independent, really, really simple formula. P of A and B equals P of A times P of B. Multiplication rule, right? Multiply together. But if it's dependent, that might take a little bit time because the formula is also multiplied, by the way. But you have to identify the order. Yeah, suppose A occurs first. You have to firstly multiply the probability of A and then multiply the probability of B given A already occurred. There's an order, right? Yeah, A occur first. So put the probability of A first and B occur because A affects B. So we have to consider the probability of B given A and then multiply them together. So that is the second formula for multiplication rule when the 2 events are dependent. Yeah, we're gonna practice. Now we're going to look at the package of section 4.2. Let's start from I circled some questions. I think that's good for us to look at together. Number 8, events that are what cannot occur at the same time. Let me close this. Okay. Events that are independent, dependent, disjoint. Yeah. So when it comes to relationship of 2 events, we learned 3 concepts, right? Basically 2 concepts: independent, otherwise it's called dependent, and disjoint and not disjoint. Yeah. Cannot occur at the same time. It's called disjoint. Perfect. Thank you, guys. disjoint. Yeah. Okay, number 9. Probability of A or B indicates what? We have 4 answer choices. A, the probability that A and B both occur in the same time. I don't think so. That's the P of A and B in the same trial. Okay. B, the probability that event A occur in one trial followed by event B in another trial. A lot of information, but no. C, the probability that in a single trial, event A occurs, event B occurs, or they both occur. That sounds right. D, the probability that event A or event B does not occur in a single trial. What do you think? C, awesome, perfect. It is C. Okay, P of A or B means the probability of either only A occur or only B occur or they both occur. Number 10. Use the data in the following table, which lists the drive-through order accuracy at a popular fast food chains. Assume that orders are randomly selected from those included in the table. Yeah, I mainly look at the table. I like to just look at the table and figure out what's going on here. So this is a table. So if I look at the row by row, I have a order accurate, I have a order not accurate. Oh, so that's the row by row, order accurate and not accurate. And if I look at it by column, I have 4 different restaurants, right? So we have 4 different restaurants. So that's what this table about. Yeah. Remember, if you have a table like that, I would do this. Too thick. I would extend the table and find the total. It won't take too much time. So this one, 362, and this one, oops, apologize for that. I think if I try to zoom in too much, it disappears somehow. So this one, if I don't, it's really hard for me to see. Okay, so this is 336. Yep. And this one is 269. And this one is 149. Right? And then now I go by row. I'm going to use a calculator to add them up. Because you have to find the total anyway, if the question doesn't give you. Yeah, I looked at all the math problems with the table in it, and you have to find the total yourself. So that's a good start to find the total of the subjects, total number of subjects. So let me add 329 with 278 with 232, 131. So the sum of the first row, 970. And now I'm going to do the second row. 33 plus 58 plus 37 plus 18, 146. That's 6. If I add them up, I have 1116. Yeah, I'll double check by doing the total of the row of the columns. Yeah, 362 plus 336 plus 269 plus 149. Yeah, I got the same thing. All right, so that's how do we know we have our sample size. Yeah, that's how do we know our sample size is 1116. All right. Yeah, in the sample we have the waters. So our subjects, our data is waters. Oh, Dustin, you already have the answer? What is 900? Oh, I know what you mean. Yeah, you are right. I got the same thing. Perfect. Yeah. So also on the bottom right, I have the total number of the values, right? Total number of the waters. Okay. So let's see what are we looking for. If one order is selected, find the probability of getting an order from restaurant A or C or an order that is not accurate. Be very careful because we see two ors. We see two ors doesn't mean you can see that as 3 events, but you know we can see that as two events. Okay, we are going to mainly deal with this or. Okay, and get a restaurant A or C, that's gonna be our first event, and get an order that is not accurate is gonna be the second. All right. Yeah, A or C or not accurate. I hope I'm clear enough about that. How do I label that? Because I already have a we use E sub 1, E sub 2. Okay, events, right? The initial is the E. So we can let E sub 1 be the orders from A or C, right? And we use E sub 2 to be the order is not accurate. So this is a problem of finding P of E1 or E2. Yeah, I like properly to label them, use capital letters to label them. Help me to thinking. It also help me to demonstrate. All right, so is it E1 or E2? Addition rule or multiplication rule? Addition rule or multiplication rule? Which rule we are going to apply? Yeah, also please look at my label, yeah, addition rule awesome, to see if it does make sense or not. Our goal is to find the probability of getting an order from A or C, or the order is not accurate. Yeah. So it actually, you know, English is very important in learning mathematics too, because we are learning mathematics in English. So you have to be able to understand the grammar and to see the structure of the compound event. All right, addition rule. Then are E1 and E2 disjoint or not disjoint? Disjoint or not disjoint? Disjoint or not disjoint? Could A or C have a not inaccurate order? Would that be able E1 and E2 happen at the same time? So disjoint or not disjoint? Not disjoint. Awesome. Yeah, very good. Then we're going to use the first formula, right? P of E1 plus P of E2 minus P of E1 and E2. You know, to make it simple, I would ask my students, do not worry about the formula, just do this. Draw a big bar, and in the denominator, we have the sample size as a denominator, right? And then since the two events are not disjoint, in the numerator, we're going to have two things. Sorry, we're going to have three things. Yeah. The first thing, how many waters favor E sub 1? Do we agree the denominator is 1116? The sample size, right? Yeah. And numerator, we're going to have three things. Numerator, we're going to have three things. The first thing, how many order is it from restaurant A or restaurant C? How many of them? 362. Let me see. A or C? Yeah, let's see what is E1 represent. E sub 1 represents the order from A or C. How many orders from restaurant A or restaurant C? Yeah, do we add them up? Should we add them? Yeah, okay, Dustin is right. Yeah, we add them up. We have 631. Yeah. Please let me know if I'm clear. If not, I'll explain again. You're gonna have a similar problem. Maybe the same with this one. Yeah, because depends on the version might be different, but the same type of problem. Yeah. And the second thing in the numerator, how many order not accurate? Yeah, E sub 2 represents the order is not accurate. Among the 1116 orders, how many of them not accurate? You're gonna look at the second row. How many of them not accurate? Awesome, 146. 146. And since they are disjoint, right? So we're gonna need one more number and gonna subtract that number. Yeah. That number gonna be the number of orders from restaurant A or from restaurant C and not accurate. And not accurate. Yeah, let's see, how do we find that? Ooh, too thick. How about I just do this? Restaurant A have 33 inaccurate or have 33 orders that are not accurate, and restaurant C has 37 orders that are not accurate, right? So how many orders they are from restaurant A or from restaurant C, and they are inaccurate, they are not accurate? Perfect. You guys great. 70. All right. Yeah, you know, I figure out this is the best, easiest way for my students. So when we look for the events of or, right? The events of the probability of or, probability of events with or, we draw a big bar, and the denominator is going to be the sample size. Numerator, if the two events are disjoint, we're going to have three numbers. The first number plus second number minus third number. Yeah, if it's disjoint, then we just get rid of the last number. Yeah, so this is very straightforward for my students to get it done fast. And now we can calculate. Let's see what do we have. Numerator 631 plus 146, and then minus, yeah, don't forget the last number is to subtract, minus 70. And numerator, I get 707 divided by 1116. I have 0.63. Yeah, you know, did I count anything wrong? 0.63. Oh, 4. Okay, rounded up. Oh, now I remember. is you must read this sentence, okay? Round to 3 decimal places. So on your calculator, you get a 0.63351254448. Yeah, since we need to keep 3 decimal places, we look at this digit. Since it's bigger than or equal to 5, we round it up, round 3 up. So the answer is 0.634. Is that doable? Yeah, 63 is fine, but if you enter that, the system will mark it wrong, and you know we have to read the sentence and round it properly. Awesome, thank you, Kayla. All right, so any question about number 10? Am I clear about this problem? Basically, you are identifying the probability we are looking for is the probability of or even, even E sub 1 or E sub 2. And then you need to be very clear, what is E sub 1? What is E sub 2? Be very, very clear about that. And then you know, since we are looking for probability of or, we need to use the addition rule. And then before we actually use the addition rule, we have to think about, are the two events disjoint or not disjoint? In this case, they are not disjoint. Then the numerator, we're going to have 3 numbers. First number plus second number minus third number. And the denominator always the sample size. This is empirical, by the way. What we learned on Tuesday is useful is the foundation of this section. Yeah, denominator is the sample size. Numerator have 3 numbers. First number is the values in the sample that favor E sub 1. Second number is the number of values favor E sub 2. Minus the third number is the number of values favor both. Yeah, so something like that. So that's number 10. If you have no questions, we're going to keep going. Let's look at this question. A what is any event combining 2 or more simple events? Okay, that's a simple concept. Compound event, all right, compound event is actually not very accurate, by the way. We should remove. Compound event is a result that combining 2 or more events. It doesn't have to be simple. Simple event means outcome. It doesn't have to be simple. Okay, next. Number 15, multiple choice question. When randomly selecting adults, let M denote the event of randomly selecting a male, and let B denote the event of randomly selecting someone with blue eyes. What does P of M given B represent? Is P of M given B the same as P of B given M? This is a very good problem. Why is it a good problem? If you know how to answer this problem, that means you understand what is conditional probability. You understand the notation for conditional probabilities. So here, M means male. B means eye color blue. So what does P of M given B represent? Yeah, the first part of the question. What does P of M given B represent? Yeah, A, B, C, D. Yeah, please take time to read them and let me know. The condition is behind the bar. Condition is behind the bar. So B is the condition. Its condition means B already occur. Means you already know the subject you pick has blue eyes. Under that condition, the probability of getting a male, right? Let's see what do you choose. The answer is not only B or C. Okay, let's see. B says the probability of getting a male given that someone with blue eyes has been selected. C, the probability of getting someone with blue eyes given that a male has been. This is B. Has to be B. C is wrong. Okay, because we are looking for the meaning of P of M given B. Yeah, please make sense of that. Again, B is the condition behind the bar. Since B is behind the bar, B is the condition. That means B already occurred. That means we already know the subject has blue eyes, right? Given that means we already know. Yeah, given that someone's blue eyes has been selected, already occurred, right? On that condition, the probability of getting a male. Do we agree? Number 15, the first part, we should choose B. B as in banana.
Yes,
Yeah,
it makes
C. Okay.
Yes, it makes sense. Honestly, it's when you started saying condition, at least for me, that I got a little bit more confused. But it makes sense once you re-explained it. Thank you.
Okay. Thank you. Yeah. So now we're gonna see the difference between P of M given B and P of B given M. Yeah, the only difference is symbol-wise, notation-wise, just the water, right? Yeah, but make a huge difference. Since the water is different, that means a huge difference. Because only the event behind the bar is the condition. All right. Yeah, which one do you want to choose? Let's see. A. Let me read A. A says no. Yeah, they are not the same. Yeah, they are different. For sure, they are different. So of course, this C is out. D is out. Yeah. And because, what about the reason? Because the P of B given M represents the probability of getting someone with blue eyes given that. Yeah. Follow given that. That's our condition. A male has been selected. Well, that's correct. Yeah, given that male has been selected. Yeah, I would say A, but then let me read B. No, because P of B given M represents the probability of getting a male. Oh no, that's wrong. So it has to be A. Yeah, let me know. Do you agree on that? It is kind of important. Yeah, this is a good problem. If you understand this problem, you understand conditional. Thank you, Charlie. What about other students? Are you guys still with me? Yeah, the online class is I don't see you. I don't know if you are just leave the, yeah, I hope you're paying attention because those questions are MyLab math questions. You have to do them anyway, right? If we do them together and then you go ahead to do your assignment, you will feel a lot easier. You will not struggle, right? Okay, number 16. Hospitals typically require backup generators to provide electricity in the event of a power outage. Outage, not outage, outage. Assume that emergency backup generators fail 19% of the times when they are needed. A hospital has 2 backup generators, so that power is available if one of them fails during a power outage. Complete part A and B below. Okay, part A. Find the probability that both generators fail during a power outage. Okay, we are looking for the probability that F1 be the first generator fail, that F2 be the second generator fail. All right? We use F. So what's the probability we are actually looking for? Are we looking for a probability of F1 or what? And this word, is this a correct connective? Because I don't see and in the question. Yeah, but you know, we have both. Yeah, so what do you think? What should I put here? What are we looking for?
It should be and.
Perfect. Yeah, and. Very good. We are looking for the first generator fail and the second generator fail at the same time, right? Yeah, even though the wording is different, but it means the same thing. Yeah, the probability of both of them fail at the same time. And that means the first fail and the second fail. Awesome. Okay, guys, addition rule or multiplication rule? Addition rule or multiplication rule?
Multiplication.
Perfect, yeah. And since we are going to use the multiplication rule, then we need to ask ourselves, are the two events dependent or independent? Dependent or independent?
Independent.
Awesome, independent. They better independent, right? Yeah, they are independent. Yeah, do not overthink. You know, some students would argue, how do you know it's independent? We want them to be independent, you know. If the first one broke, the second one broke too, then what's the point? So we want them to be independent, then we can have backup, right? Yeah, independent for sure. If they are independent, then we use the first formula in the multiplication rule, right? It's going to be f of p of f sub 1 times p of f sub 2. Yeah, good news is if it's independent, we do not have to handle conditional probability. Simply just multiply the two probability together. Okay, what's the probability of the first generator fail? What's the probability that first generator fail? %. Awesome. In decimal? Yeah, you know how to convert to decimal, right? 0.19, yeah. And what's the probability that second generator also fail? Same thing, right? They are probably the same brand, or you know. Also 0.19, yeah. There's a arithmetic part. Arithmetic part we might not spend. We will not have time to spend too much time to show how do we convert from percent to decimal, something like that. But if you need help, you can email me. We can make a schedule and I'll explain that. So multiply 0.19 by 0.19, I have 0.0361. And you know what? I would the answer is decimal, but I want to convert it back to percent. Then I have a better understanding about the chance of both of them are fail. That's horrible. That's not going to be good things, right? 3.61%. The answer in decimal is 0.0361. That means both of the generators fail at the same time. The chance is 3.41%. If I round up, it's 4%. That's not good because it's a hospital. It's not some other commercial store. It's a hospital. That means in 100 times outreach, 4 times of them have no electricity. When patients sometimes very urgent, they are waiting for being saved, you know. So I would say that is not good enough. Oh, hold on. That's another thing. B, part B. Find the probability of having a working generator in the event of a power outage. Is that probability high enough for the hospital? Assume the hospital needs both generators to fail less than 1% of the time when needed. Yeah, that's the standard. That's the standard, less than 1%. Then that's not too bad. Okay, so now we are looking for another probability. What? The probability that the hospital can run its business. Right? You rewording the here. What's the probability of the hospital have a working generator? That means the probability that both of them fail did not occur, right? You see what I'm talking about? Is that event the complement of F1 and F2? What's the complement that the hospital have a generator? At least one generator. The complement the hospital at least have one generator is no generator. So we just got the probability of no generator. So the probability of at least have one generator would be the complement, would be 1 minus 0.0361. Awesome, exactly. Just use 1 to minus that, right? And that's what we learned on Tuesday. And you see those two probabilities must add up to 1. I think most of you probably understand this. Am I clear? Can you please ask questions if it's not? Okay, the last part, we're almost done, is C, okay? This hospital is not well equipped because the chance for both generators fail is almost 4%. So that is a lot higher, 4 times higher than the standard. So this hospital needs to be improved, right? Okay, we did cover both addition rule and multiplication rule, and also the last part we use the complement. So we cover them all. Yeah, that's this section. If you have any questions, you are welcome to email me, and we can meet during my student hour, and we can work on your problems together. All right? And I'll see you on Tuesday. Have a good night, guys. See ya. Bye-bye.